So let's, this is a brand new project that I just opened. We'll just choose some inputs and outputs. Yeah, let's do analog balanced, one channel, just loop back. And I think that's about it. Sorry. And then we'll look at the FFT analyzer. And we can, let's see here. What I will do is, so I'll choose a sample rate that is an even number like 192K. So with a bandwidth of, let's say 22 kilohertz, that uses a sample rate of 48 kilohertz. And then, so I've chosen an FFT length that is 24K. So if I set my generator here to a sine wave, let's make it 1 volt at 1 kilohertz. And just go ahead and do an FFT with the default setting. So this is the default window here. Let's see, where's the window? AP equiripple. So just to give you an idea of what happens if I choose no window. Let me actually, before I do that, let me go back to the equiripple and I'll do a few averages. So let's just do 5 averages and power averages. And we can look at this in dBV. So the 0 dBV is 1 volt. So that's the default equiripple window. If I turn the window to none, we can do an append here. And you can see we're getting this behavior that we looked at in some of the slides. So we're not able to resolve the noise floor very well. Could actually be worse than that because the sine frequency that I'm generating is 1K, which is a submultiple of the sample rate. So if I choose something like 997, it might actually be worse. I'm not sure about this. This is just a hunch, so let's see what we get. Yeah, there you go. So the sample of 997 hertz is even less synchronous with the acquisition buffer than the other sample. Now if I look at the underlying data, I have FFT length of 24K, and if I want to see what the actual bin width is, I can look at the data table here, and by default the number of points displayed is the same as the graph. To look at the underlying data, I have to choose all points. And you can see the first bin is at 0, and so the bin width here is 2 hertz. And I've chosen a signal at 997, and it's totally asynchronous with the acquisition length. So I'm getting this very scalloped appearance. Now if we look at, one of the other ones I talked about was the flat top window. And let's do a measurement with that. So here's the flat top window. Now if I zoom in, you'll be able to see some behavior, what the window looks like in terms of side lobes. So you can see the equiripple window has much lower side lobes than the flat top. But what's kind of interesting here is if I was trying to measure the amplitude, the flat top is a very good choice because it's very flat at the top, and I can change the frequency and still get a very good estimate. So let's look at the generator here and change this to something like 9975. Do another measurement. Let me zoom in even more. So you can see I'm still getting a very good estimate of the peak. And you can go all the way to the close to the edge of the window, edge of the bin, and you'll still get a good estimate of the peak. So for an application like using a sound level calibrator, the frequency is nominally, say, 1 kilohertz, but it could be off by 1 or 2 hertz. And if you're trying to calibrate your microphone, this would be a good way to do it, because the peak of that FFT gives you a very good estimate of the signal, regardless of where it is relative to the center frequency of the FFT bin. Any questions on that? So let me zoom out to original here, which is this one, I think. And let's see. I'll delete some of these traces that we don't need. So let's, well, I can just take them off, I guess. Yeah. Actually, we'll leave that one on. No. Okay. All right. So if you want to see what some of the other windows look like, we can choose Blackman-Harris 3-term. So that's close to the equiripple. Blackman-Harris 4-term. Not a lot of variation there. Dolph Chebyshev. Then we have Dolph Chebyshev 200 dB. Now I'm not even sure what all these windows are used for. I know that recently with our digital serial interface, we added the capability to analyze and generate 32 bits of audio. And when that was done, our DSP engineer added these extra windows, and I'm not even sure what they're used for. Here's a Dolph Chebyshev 250. And then we have the, we looked at the flat top, and finally we have the hand window. The hand window is very commonly used. I used to work in noise control and vibration analysis using signal analyzers. And most analyzers had a Hanning window. They called it Hanning, same thing. So let's see what that one looks like. Yeah, so that would be this one here. Yeah, I don't see a whole lot of difference. Okay, so these are the topics we're going to look at in this presentation on jitter modulation. So what is jitter? Jitter as it affects the audio signal. Intrinsic jitter, sampling jitter, jitter in the digital interface, J-test, jitter tolerance, intersymbol interference, noise-induced jitter, synchronization jitter in analog to digital converters, the jitter transfer function, and how it's implemented in our APX 500 software. Now, most of the information in this presentation pertains to the AES3 or the SPDIF interface. But we do have jitter on other modules as well. So our digital serial input-output interface can have jitter applied to the clocks that are supplied to any device. And we will be adding jitter for other modules in the near future. Okay, so what is jitter? Jitter is the variation in time of an event from its expected time, and it occurs with clock signals and with transmitted data. So if we look at the graphic here, we would like to see these pulses lining up one on top of the other exactly, but as you can see, some of them are scattered in time a little bit, and this causes variations in sampling of the time when the audio waveform is sampled. So it affects the digital audio in two ways: at sampling instance in time and during data transmission over an interface. And this can produce audible artifacts. So jitter on a clock determines the sampling instance, and it modulates the signal timing. This produces sidebands in the FFT spectrum. And the frequency spectrum of the jitter sidebands corresponds to the jittering in time. So this shows the FFT of an audio signal. So it's a 10 kilohertz signal with sidebands from 3 kilohertz jitter modulation. So this is probably an analog to digital converter, and we're applying a sine wave at 10 kilohertz, but we're jittering the clock with a sinusoidal jitter at 3 kilohertz. And you can see these sidebands are 3 kilohertz away from the fundamental, and then we have other sidebands that are spaced another 3 kilohertz away from that. So this is a classic example of jitter on a device. So for measuring sampling jitter, there are two approaches. You can measure the jitter on a clock that's close to the sampling point, or you can measure the effect on the audio. Now, it's not always possible to do number one, to measure the jitter on a clock that's close to the audio. So sometimes you have to resort to item number two, to measure the effect on the audio. Okay, so we saw a graph like this earlier, which had the eye pattern on an oscilloscope, and this is an example of an eye on the eye opening on a signal that is much more degraded than the one we saw earlier. As you can see, it's barely recognizable. So this one would probably have severe problems. Now, intrinsic jitter has its source within the device itself. It's not jitter introduced into the digital signal interface or in the synchronization input. Sampling jitter can occur in both the A to D converter and the D to A converter sampling processes, and even in sample rate converter processes, which may have no physical clock. So here, what we're looking at in the scope display is a sine wave being generated, and the signal in red is what we call the residual. So once you pass the main signal through a notch filter, what's left, you take away the fundamental sine component, and what's left is the residual. And you can see the effect of a jittered waveform on the residual. And this will also show up as these sidebands in the FFT spectrum. So by looking at, to measure the effect of sampling jitter by the effect on the audio, you don't need to probe any clocks. You just look for the effects in the FFT spectrum. And this can work with asynchronous sample rate converters. The jitter transfer function is a measure of the relationship between the input and output jitter, or the jitter gain versus frequency for a device. So if a device has a digital input and a digital output, you would like it to not increase the jitter as it passes through the device. So this, for digital-only devices, we can measure this transfer function by jittering the signal and measuring how much output jitter we get for a corresponding amount of input jitter. So in this graph, you can see that the device is very flat with a zero gain. But starting at about 1 kilohertz, the gain starts to increase, meaning that the device puts out more jitter than comes into it by a small amount, which is not desirable. And then at high frequency, it just starts to roll off altogether. Jitter can be introduced to the digital interface signal through several mechanisms, usually related to cable losses. Now there's a phenomenon called intersymbol interference that we're going to talk about. So intersymbol interference and noise-induced jitter are examples of interface jitter. these are illustrated in the next few slides. So intersymbol interference is a cause of jitter, which is a consequence of the varying pulse lengths of the digital code and the reduced rise time from cable losses. So as we talked about earlier, depending on the pattern of zeros and ones and preambles in the signal, you can get capacitance, charge builds up in the cable, and this will cause errors in the sampling instances, which cause errors in the samples, the estimate of the sample that's acquired. There's also noise-induced jitter. When the digital signal can maintain a very fast rise time, noise pickup from the interface causes very little jitter. However, when the rise times are sloped due to cable losses, so instead of being a nice square wave, the wave is leaning over like this. In this case, noise on the signal can change the sampling instances and cause jitter that affects the signal. So the noise rides the signal transitions, moving the zero crossings and creating jitter. There's also synchronization jitter in A to D converters. So if an A to D converter has a sync input for time alignment with other equipment, jitter can be coupled through this input to the A to D converter clock. So in places like broadcast studios and recording studios, they'll often have a house clock that they run along, and they synchronize all of the digital devices within the house. And if there's jitter on that clock, it can introduce jitter into other devices that are connected. Synchronization jitter can be attenuated with a phase lock loop, imposing the characteristics of a low-pass filter on the synchronization signal. Now, I mentioned earlier the J-test. This is an AES-3 test signal that was developed to maximize the coherence of data patterns while at the same time providing a basic high-level stimulus tone. This test stimulates the worst case levels of data-induced jitter. We have a tech note on this, which talks about measuring the J-test signal with our APX audio analyzers. That can be downloaded from our website. You can see here, this is the results of the J-test signal and the sidebands, which are showing up based on the effects of this jitter-induced signal from the J-test signal. Jitter tolerance is the maximum level of jitter which a digital audio receiver can accept before it starts to produce errors. The AES-3 specification defines a jitter tolerance template representing a lower limit for receiver jitter tolerance. So here we have the peak-to-peak amplitude of jitter in terms of unit intervals. This goes from 100 milli-UI to 10 milli-UI. There's a transition here at 200 hertz. It slopes down to about 8 kilohertz with a level of 0.25 unit intervals. So in the AES-3 jitter test, you would generate this level of jitter at different frequencies and check to see that the device does not lose lock or produce any errors. So there's a different jitter tolerance for consumer devices. Here the frequency is shifted down by a factor of 40 to allow the use of narrowband recovery, or VCO or VCXO. So here you can see it's 10 UI from 1 hertz to 5 hertz, slopes down to 0.25 UI at 200 hertz, and then it's flat out to, what is that, about 400K, and it's down at 0.2 UI. So in the APX 500 analyzers, with the APX 555 that we just launched this past year, we have the ADIO, or Advanced Digital I/O interface. So this has balanced AES-3 input-output, unbalanced SPDIF, and optical. The interface includes output impairments and input measurements. And there's a jitter generator and jitter demodulator. These are some of the output impairments you can use. So for audio settings, of course, you can set the sample rate, the bit depth, and whether dither is enabled or not. We talked about that this morning. For impairments, you can change the digital pulse level in volts peak to peak. You can invert the pulse. You can vary the rise time. The choices are fixed, variable, so you can just type in the rise time within certain limits. Or there's a mode called cable simulation mode, which puts in a fixed amount of impairment of the rise time of the signal to simulate a large length of cable. You can introduce a common mode sine signal to the balanced interface only, and you can add noise to the physical signal, the interface signal. And then you can adjust the user and status bits that we looked at this morning. You can force parity errors, and you can also change the validity bits. So here we have a look at the output impairments in terms of rise time. So the top graph is a fixed rise time of 12 nanoseconds. Here we have the cable simulation mode, and then the custom mode, and you can vary the rise time from 12 nanoseconds to 100 nanoseconds. This is the common mode sine for output impairments. So in this case, we have a balanced cable, so there would be a twisted pair inside the cable, and one side of the interface is positive going, the other side is negative going, and it's a differential interface, so it takes the difference between those two signals, and interference can come in. So we can test the common mode signal rejection on a balanced digital input. So this top chart is a 2 volt to peak digital interface pulse with 2 volts peak to peak of common mode sine. And the bottom trace is it's a 0 volt peak to peak digital interface pulse with 2 volts peak to peak of common mode sine. So it applies an interfering sine wave equally to both sides of the balanced connection to simulate common mode noise interference. We also have the ability to add noise to the interface signal, and that's to test the noise rejection capability of a digital device's input. So there's an interfering random white noise of variable amplitude applied to the serial bit stream. The noise is added at the BNC output, and it's added as normal mode signal, not a common mode signal, to the XLR, balanced XLR output. So you can see in the red trace here, this is what the interface signal should look like, and the blue trace shows that we've added random noise to the interface signal. These are the specifications for the APX Advanced Digital I/O Output Impairment. So the characteristics, the variable rise time, the range is 12 nanoseconds to 100 nanoseconds with 1 nanosecond typical resolution. The accuracy is plus or minus 10% plus 2 nanoseconds. Cable simulation approximates the signal degradation of 100 meters of cable type Belden 1696A. That's the standard digital cable. The normal mode noise is a pseudo-random pulse train. And on the unbalanced interface, it's 0 to 635 millivolts peak to peak in 2.5 millivolt steps with accuracy of plus or minus 10% plus 25 millivolts. The balanced is 0 to 2.55 volts peak to peak in 10 millivolt steps. The common mode signal on the balanced only output is a sine waveform. The frequency range is 20 hertz to 100 kilohertz, and the amplitude range 0 to 20 volts peak to peak in 24 millivolt steps. This is a view of the jitter generator panel in the APX software. So you choose, have a choice of sine, square, or noise. You have the frequency of the jitter signal and the peak level of the jitter signal, either in units of seconds, nanoseconds, or unit intervals. And of course you can apply an equalization curve for these jitter tolerance tests. So if you want to run the AES3 standard jitter tolerance test, you would load a template for that curve into this EQ and apply that. You can see the effects of the jitter on this waveform here. Rather than the pulses being one on top of the other, they're jittering back and forth in time randomly, or depending on the waveform of the jitter. Here it's a sinusoidal jitter, so they'll be jittering back and forth as a sine wave. The output jitter specifications. So the residual jitter is an estimate of how much jitter the instrument generates when it's not trying to generate jitter. So for the unbalanced and balanced, from 700 hertz to 100 kilohertz bandwidth, there's less than 600 picoseconds of jitter. And from 50 hertz to 100 kilohertz, there's less than 1 nanosecond. And then on the optical, typically less than 2.5 nanoseconds at sample rates less than 96K. Now for output induced jitter, with a sine wave induced jitter, the frequency range is 2 hertz to 200 kilohertz, and the amplitude is 0 to 10 unit intervals, a jitter frequency less than 200 hertz. Above 200 hertz, the maximum allowable jitter decreases in a 1/f fashion to 0.2 unit intervals at jitter frequencies of 10 kilohertz and higher. The amplitude resolution is 1 nanosecond, and the accuracy is 1 kilohertz. The accuracy at 1 kilohertz is plus or minus 10% plus 1 nanosecond. The jitter flatness is plus or minus 0.5 dB from 100 hertz to 80 kilohertz. And the jitter spectrum, spurious products are typically minus 40 dBc below the jitter signal, or minus 60 dBui, whichever is larger. So on the ADIO inputs, supplies to the balanced, unbalanced, or optical. The bit depth is 8 to 24 bits. We have, we can adjust the termination impedance on the input. And you can choose to measure either audio or jitter. So with a digital signal coming in, if you want to look at the audio signal, you choose audio. If you want to look at the jitter on the audio signal, you choose jitter, and then you can display the jitter level, the jitter frequency, or look at the FFT of the jitter just as if it was an audio signal. The jitter filter is built in. There's a high pass 700 hertz AES3 or 50 hertz. For low pass, there's Butterworth or elliptic at a user specified frequency. And then the weighting available are the standard weighting filters, none, A weight, B weight, C weight, CCIR 1K, CCIR 2K, and so on. So the ADIO input jitter measurements, this requires the advanced master clock. So the APX 555 comes with the ADIO module standard and also the advanced master clock. If you have an existing instrument that does not have the ADIO, you can get the ADIO and the advanced master clock as an option. You can either purchase them together, which you would need if you wanted to do jitter analysis, jitter generation analysis, or you can buy them separately. So we can look at the jitter waveform here. In this case, rather than looking at the audio, we're looking at the waveform of the jitter signal. We're also looking at the spectrum, the FFT of the jitter signal. And then the meters on the front panel, we can look at the jitter RMS level, the average level, the peak level, crest factor, bandpass level, the frequency, and the distortion. These are the specifications for the ADIO input jitter. So the jitter measurement range is 0 to 4 unit intervals at jitter frequencies less than 500 hertz. And the detection is peak, RMS, or average. The supplemental information here, above 500 hertz, the maximum allowable jitter decreases in a 1/f fashion to 0.2 unit intervals at a jitter frequency of 10 kilohertz and higher. And peak detection must be used for residual measurements per AES3. Average detection is recommended for jitter response measurements. For the bandwidth, we have high pass of 50 hertz or 700 hertz, AES3, and low pass of 1K to 150 kilohertz. The accuracy at 1K is plus or minus 10% plus 1 nanosecond, flatness plus or minus a half dB, and we already talked about residual jitter. So I think that's the end of the slides. We could do a little demonstration here. So I wanted to show you this. This is a document called the Tech Note. It's kind of an application note, and we have several of these on different topics available at our website, audioprecision.com. This one was developed by my colleague Steve Peterson when we launched the APX 555, and it's really excellent. I knew of it, but I didn't get a chance to look at it in detail. I read it on the plane on the way over from the United States here to Korea. And he provides a number of example projects that you can use to analyze A to D converters and D to A converters. So on Sunday in my hotel room, I used this little box. This is it's an old combination of A to D converter and D to A converter that we had in our lab, and I borrowed a 555 from JH. He was kind enough to bring it to my hotel, and I played around with these projects, and they're really very good. So there are project files in here for analyzing DACs and ADCs at 48 kilohertz and 96 kilohertz, and there's quite a large number of tests. So some of those tests involve jitter, and what I'll do for a demo is just run through one of those. So let me see if I scroll down a little bit. So we'll probably look at these project files a little more tomorrow, but I just wanted to digital analog converter. Yeah, okay. Maybe we'll just do this one live. So I'll just go into bench mode here. So I have the digital input connected to the SpeedIF out, digital unbalanced out, and then the analog output from the DAC is going into the analog inputs. So we'll just choose digital unbalanced, 48K, analog balanced, 2 channels, and let's see here if we get any signal. Let's see. If you want the device to work, the first thing you have to do is turn the power on. Okay, so it says the device is picking up 48 kilohertz signal. Okay, there we go. So here we're just generating a sine signal at 1 kilohertz, minus 1 dB relative to full scale. You can see the frequency here. The THD plus N ratio is quite high. You might knock this down a little bit. Try something like minus 20 dBFS. Most devices behave pretty well at that range. And if I look at the clocks, okay. So you can see the signal there. So this is how I would apply jitter to the interface. So you can you have a choice of applying the jitter to the digital output or to the reference sync. So there's a sync output on the back that you could use to synchronize a device that has a sync input. Here we'll apply it to the digital interface, and you have a choice of waveform, sine, square, or noise, and jitter frequency. So let's just try peak level of 1 UI, turn on some jitter. And you can see the effects of the jitter there. Some sidebands coming in. There's an EQ curve applied here. Let's try turning that off. And as you increase the magnitude of the jitter, you can see that harmonic at 2K starting to creep up. And of course you've got the THD plus N ratio is at minus 61. If we turn the jitter signal off, it goes back down to minus 70. So you can apply different levels of jitter here. And you can also change the waveform. If we look at a square wave, yeah, so the signal goes away completely. I don't think it likes the square wave jitter very much. Try backing down the amplitude or the peak level of the jitter. Yeah, there we go. So at 100 milli UI, or a tenth of a UI, we're getting some signal with the square wave jitter. But you can see a lot of these harmonic components coming in. So the device really does not tolerate square wave jitter very well at all. We can try a noise signal as well. And seems to be less susceptible to problems, although it's just gone unstable. And usually what happens is there's an error light on the front of the device, and you can see the LED flickering, indicating that it's having trouble. It's going out of lock. So if we go back to sine, so that's the effect of the jitter on the analog signal coming out of the D to A converter. And I believe there's a project in the there's a test in the D to A converter project, which we can look at. Yeah, so let me load the A to D converter project. So these projects, as they're shipped, they're set up for a balanced digital output. And I didn't have a balanced digital cable, so I used a SpeedF. I just had to change the output inside the project. So yeah, as you can see, there's a number of signal paths here. There's a channel 1 and channel 2 signal path. We'll talk about this a little bit tomorrow, but there's another signal path here called output jitter. And let's just have a look at the inputs and outputs. So this is an analog to digital converter. So the output connector is analog balanced. The input connector is digital unbalanced in this case. And let's look at the monitors here. So just verify connections. So what we're actually looking at the jitter signal right now. So if we look at the audio signal, yeah, so it's set to minus 20 dB relative to the full scale output. So you can see the signal here. And what this test does is, it looks at instead of looking at the audio, we can look at the jitter in terms of unit intervals or seconds. So essentially we're measuring the jitter level coming out of this analog to digital converter. While generating a signal at 1 volt RMS with a frequency of 997 kilohertz. And then we can also look at the jitter spectrum. So this is the jitter level in unit intervals versus frequency. And we're looking at frequency range from 20 hertz to 100 kilohertz. So you can see artifacts of the jitter. Peak component here is close to 100K at about 800 micro UI, or 0.8 milli UI. So fairly low level intrinsic jitter.